Okay, we're going to start first of all on power generation. Some of you have had AIT 1002, the power development class. Talked a little bit about three-phase power, but I want to go in and kind of review this just a little bit because, again, if we're going to run a three-phase motor with three-phase voltage, we really need to know where's that voltage coming from, how's it produced, okay? And that'll, again, as I said in the previous video, that'll give us a better shot at troubleshooting and understanding and also diagnosing problems that we've got going on with the motor. So first of all, I want to talk about a little bit about where three-phase power comes from. Well, it naturally comes from power generation stations, such as in our area in Western Kentucky region. It's the Big Rivers power plant is one of them. You have TVA, a Paradise plant. We also have a hydroelectric plant by the lakes as well. So those are all power generating stations. And as you can see, this is the inside of a power plant. These are three phases of generators right here that are being run. Okay, and basically what's happening here is we have a turbine that spins a generator. That's in the simplest terms. Okay, now we might take coal, or we might take nuclear power and heat water and create steam that goes across the turbine and spins and is coupled to the generator and spins it and creates the electricity. We also might use hydroelectric power to spin that turbine as well. Regardless, we have some moving force that will turn the turbine, that will turn the generator and create our three-phase voltage. Okay, now bring it back a little bit further. Basic principles of creating electricity. Anytime you have a wire, just a standard piece of wire, okay, and you move that between two magnets, okay, for example, a horseshoe magnet, okay, anytime I move that wire between the horseshoe magnet there, that wire is breaking the magnetic lines of flux going across from one side to the other, okay. Anytime we do that and we break those lines of flux with a piece of wire, we induce a voltage in that wire. So if I had a piece of wire with a voltmeter on it, and I was able to move it in and out of that magnetic field, we would see some type of deflection of or reading on the voltmeter. Okay? Now at the same time, if we have a magnet and we move it around coils, okay, we induce a voltage in those coils. So with our rotating magnet like this, if we have coils here and here, for example, every time it passes by, it's going to induce a magnetic field and it's going to create a voltage in those coils. Here's a quick example. All right, so we've got two coils of wire, and again, a coil is just a single piece of wire wrapped around and around. And when we wrap it around, we pass that magnet by it, we induce a voltage. So we get a positive voltage on this side, on the north side, and a negative voltage on the south side. And as it rotates, it gives us a positive and negative sine wave. Okay, that's how we get our sine waves. That's how we get our voltage delivered. Now this is just a single phase right here. Okay. This little file right here will show you, this is your wire right here, and this is your magnet, okay? And this is in the most simple terms. This is not how the power plants do this. They don't use giant magnets like this. But what this illustrates is that when you pass that wire through the magnetic fields, lines of flux right here, when it's breaking those lines of flux, we start to get peaks in our sine wave right here. We create a peak voltage, drops down to the negative when it's 90 degrees. It'll be in the negative, or excuse me, no voltage at all. And then when it rotates 180 degrees, it will come down and peak negative. You can see our voltmeter over here going to negative, and then to the zero plane, and then positive. So this is creating a voltage. This is just a single phase. This is the most simple type of generator. It just gives you an illustration as to how we create that power. Now, if I add another set of coils that are 90 degrees from each other, I'm not sure how well you can see this, but this would be the A set of coils that are wired in series, and you got your B set of coils that are wired in series together. Okay? If I've added another set of coils 90 degrees from each other, then we get a second phase. We have an A phase that's going like this, and then 90 degrees later, on our line here, 90 degrees later, we have a B phase. Okay, so now we've got two phases. Well, it stands to reason that if we add a third set of coils and we put them 120 degrees, 123 electrical degrees apart from each other, we're going to have three phases. And you can see the three phases. The blue phase is phase A, the green is phase C, and the red is phase B. Okay, and as each one is peaking, like for example, when phase A starts to peak, okay, it starts to drop off a little bit. phase C is coming on, and it's getting a little, and it gets stronger, and before it can drop off to the zero plane, you have phase B kicking in here. So we get a nice smooth ripple effect coming out of the power plant, and that's what these are the power pulses, you might say, that the motor experiences. So we're connected, we can consider this the Big Rivers power plant or Paradise, whatever you want to call it. And they're generating it. We've got 3 lines coming down from the transmission lines, and they we'll connect this to our motor. Now, it's coming out of our power plants at a much higher voltage. We'll have to step it down to probably like 480 volts for our motor. But my point is that this is where it's being generated and how each 3 phases are being generated. And of course, we connect these 3 phases to our motor, and you got a 3-phase motor system right there, okay? Again, it's another example. You see the rotation and the magnetic fields as they pass the coils. It peaks, and it directly aligns with the coils. It peaks with these, and aligns with this, these sine waves, and these sine waves peak right there as they align. As they're 90 degrees from each other, or if they're 90 degrees out of alignment, it's going to be along the zero plane, producing no voltage at all. So that rotation, okay, is what we're looking for. That's what helps create the 3 phases. Okay, just another example. Okay, there's the 3-phase sine waves, and notice again, this is very important, 120 electrical degrees. That's because our coils are 120 electrical degrees apart from each other. Okay, so what determines how much voltage is produced? Well, a couple of things. Number one, the number of turns in our coil. How many times we are wrapping our coil around our pole piece right here, okay? And the other one is the diameter of wire that we use. What's the diameter of this wire, okay? The more turns and the greater the diameter of the wire, the higher the voltage, or the more voltage we'll produce with each revolution of our rotor, okay? And of course, one other factor that's very important is the speed at which we turn this rotor, the speed at which we let the magnetic field pass by these coils, okay? And we have a very standardized speed at which our power is produced. It's 60 hertz. That means that each phase comes out of our generator 60 times a second, okay? We have 60 hertz. If you look at your home, you'll see a lot of your appliances and things are rated for 60 hertz. That's because in the United States, we create power at 60 hertz. In Europe, Canada, and other places will sometimes produce power at 50 hertz. Okay, that's just what their grid's set up for. That's how they do their thing. But this, in the United States, we're at 60 hertz. Okay, so just kind of wrapping things up real quick. We produce the 3-phase power out of the power plants. Like I said, whether it's nuclear or coal or whatever is creating steam into a boiler that turns a turbine, or if we're using hydropower, excuse me, to turn that turbine. Regardless, we're getting a rotation of our generator's rotor on the inside, and it creates the 3 phases of power. Comes out. We step it up because we want a very, very high voltage transmitting down the lines that we see going down the highway. You look up and you see these 3 phases, these large towers, 3 sets of wires. Those are 3 phases going down the road that you're seeing. And the more we jack the voltage up, the current comes down. Okay, they're inversely proportional. Voltage and current are inversely proportional. So the higher the voltage, the lower the amp. That gives us the opportunity to run smaller cable with less line losses down the road and to wherever we're trying to go to. If we're going to our residence, or whether we're going to a switch yard or a substation, excuse me. But we jack that voltage up with a step-up transformer out of the power plant up to, in our example, 400,000. Me personally, I have worked with 161,000 volts that came out of the power plant over to an aluminum smelter I worked at several years ago. And so I've dealt with almost 200,000 volts. But like I said, the more we can get, the higher voltage we can get up there, the lower the current. That's less copper that they have to run, the smaller diameter copper that they have to run down the line. So that makes it more expensive. And also you have less line losses. But we jack it up, we run it down the road to some type of a substation that you've probably seen. They usually have the fences around them. They got switch gear in there. And what they're doing is they're bringing a very high voltage in there and stepping it down to where we can run loops around our residential area, somewhere around 13.8. Sometimes it's 7,700 volts, but they'll run it down to a transformer that's on the pole of our near our homes. And of course, they run it to our houses. That's usually coming in at 240 volts. But that's how I just want to kind of give an illustration where the three-phase is produced, how it's produced, and how it is that we magically wind up with it coming out of an outlet in our wall when we go to hook up our motors, whether they be in the plants or here in a lab. So that's just a general wrap-up of what three-phase voltage is. You know, like I said, you want to make sure you take notes, and there's some reading material on how this is created as well. So make sure you take care of that stuff. If you've got any questions, by all means, come see me. And so now I think you want to move on to the three-phase motors. Okay, we've created the power. Now let's get to taking the power and making the motors run.